Have you ever kind of stopped and wondered what's really going on when you write just a single line of code? How does a computer actually see those characters and somehow understand what you mean? Well, today we're going to explore that quiet, really elegant transformation from simple text into a structured idea that a machine can actually work with. So how does this happen? How does a computer look at an expression like the one you see here and see not just letters and symbols, but a whole series of operations to perform in a very specific order? That's really the core question we're looking at, because getting this right is just fundamental to how pretty much everything works, from compilers to the code editors we use every day. Okay, so the very first step in this whole process is to create a direct, totally unfiltered map of the code. It's all based on a really strict set of grammatical rules. You can think of it as the most literal blueprint imaginable.
And this initial structure, it's called a parse tree, or sometimes you'll hear it called a concrete syntax tree. That word concrete is so important here. This tree doesn't interpret a single thing. It just records the exact grammatical structure. It captures every single symbol, every parenthesis, every operator, exactly how you wrote it. This is actually the foundation that things like syntax highlighters use to color your code correctly.
And just look at how detailed this thing is. For this expression, a index plus 2, the tree has nodes not just for the variables and the numbers, but even for the square brackets themselves. All this extra detail, it's grammatically necessary, for sure, but it doesn't really add to the core logic. It's often called syntactic noise. It's a perfect representation of the grammar, but it's not yet focused on the meaning of what's happening.
Right, so to get closer to what the code is actually trying to do, we need to strip away all that noise. We've got to distill the code down to its core meaning.
And that brings us to the abstract syntax tree, or AST. This is such a crucial step for tools like linters or even those automatic code formatters. See, they don't really care about the specific symbols you used. They care about your intent. The AST represents the program's abstract meaning by filtering out all those syntactic details to focus purely on the operations and how they relate to each other.
And this slide just perfectly illustrates the difference, doesn't it? The brackets are gone. Instead, there's just a single subscript expression node. The tree no longer represents the symbols for accessing an array element, it represents the concept of it. It's just a much cleaner, more essential representation of what the code is trying to say.
Okay, so we've moved from the literal syntax to the essential meaning. But can we make this representation even more efficient? Especially when our code has parts that repeat themselves. Let's look at that expression from the beginning again. A plus A times B minus C plus B minus C times D. Just take a second and look at it. Do you see how that little part, B minus C, shows up twice? A standard AST would just create two identical branches for it, which feels a little bit redundant, right?
Well, this is where the Directed Acyclic Graph, or DAG, comes in. A DAG takes the AST one step further, and this is absolutely critical for code optimization. It identifies those common subexpressions, and instead of duplicating them, it just creates a single node and points to it from all the places it's used. Notice how the node for B minus C is calculated once, and then its result is just reused. For a compiler, this means way less work and, ultimately, faster code. It's a wonderfully elegant way to make the whole structure more compact and efficient.
So let's just pull back for a moment. This progression that we've just walked through, it isn't just a technical process. It's a way of thinking in trees. It's a beautiful little journey from raw, messy data to a refined, efficient understanding.
So really, the crucial point is this three-step journey. We start by capturing every single literal detail with a parse tree that helps tools understand the grammar. Then we abstract away the noise to find the essential meaning with an AST, which lets tools understand the logic. And finally, we optimize that meaning by reusing common ideas with the DAG so compilers can make our code run a whole lot faster. It's this powerful pattern that underpins so much of the software we use every single day.
Ultimately, these structures show us that even in the very logical world of programming, there's this kind of hidden poetry. It's a process of refinement, of finding the elegant essence inside a complex instruction. It really makes you wonder what other beautiful structures are hidden in plain sight in the tools we use every day. Thanks so much for joining me on this little exploration.